further distances, the gravitational pull becomes constant at massive distances.
Mm-hmm.
So it's like there's something else out there pushing.
Mm-hmm. Interesting. And one thing that the book goes through, and I'm not gonna go through and solve this one because it's kind of cool to look at, but one thing they consider is, an object shot from the surface of the Earth. So the first object would be just the Earth. The second object would be this projectile. And by a projectile, a point mass shot from the Earth. And the question is, without anything except the gravity from the Earth acting on it after the initial launch, what is the velocity needed to eventually leave the Earth's atmosphere, so to escape the gravitational pull?
5 meters per second.
G, because just the surface would be what you would need, right?
Oh.
Yeah, it's 5 meters per second.
Well, G is an acceleration.
Okay.
Right. Well, I throw something up at 32 feet per second.
Gotcha.
That's not per second.
Yeah.
Yeah.
I thought you guys would be happy with it.
Yeah. So it's not an acceleration. Once I throw something up, the only force acting on it is gravity. The velocity is going to decrease. So the question is, what is the velocity required for the object to escape Earth's gravitation? Okay. One thing, the way they describe it is, you need, if you take that velocity function, you need the velocity, it has a sign attached to it, you need the velocity to be greater than 0 forever. In other words, that object cannot turn around, because once it turns around, it starts slowing back down, the velocity is negative. So you need the velocity to be positive. So here in this case, little r would just be the distance from the object to the center of the Earth. So not just to the Earth's surface, but to the center of gravity. Okay. So one thing to note when going through this argument, the r, right, distance from the object to the center of the Earth, that's obviously going to be changing. Another way of putting it, the velocity has to remain positive, is that r, the distance from the object to the center of the Earth, has to always be increasing, right? So the velocity will be positive. And r at 0, this is what I didn't catch in this argument, r of 0 is what they're calling capital R. So that's the constant Earth's radius. So the distance from the center of the Earth to the surface where this projectile is shot. So the initial distance from this object to the center of the Earth, well, that's just the radius of the Earth. And the Earth's radius is roughly, according to the book, 6.38 times 10 to the 6th meters. Okay. And M, take capital M to be the mass of the Earth, which again is pretty large. That's about 5.975 times 10 to the 24th kilograms. Okay. So if you put that into the equation, force, and let's start a new page. if I replace the force over here, F, with m times a for acceleration, which is dv dt, equals g capital M little m over r squared. And this little m, this is the force of the gravity on this little object. The little m will cancel out. And we get dv dt, which dv dt, the rate of change of velocity is acceleration. That's the second derivative of r here.
Which means dt squared. D
Oops,
squared, right?
yes, that's dt. All right, and why there's a negative in this? If we assign a force, the force of gravity coming down negative. If it's this object, we say the force is negative, it's coming back down to Earth. So we get negative all that, negative gm over r squared. Okay. And this is a second order differential equation. And it's missing the independent variable t. It's one of those ones at the end of chapter 1.6. So it's second order, it's not linear. We haven't talked about second order linear anyway. But it's second order, and it is missing the independent variable. So at the end of 1.6, they talked about methods of a second order, and these are reducible. Second order, where either the independent or dependent variable is missing. And this is the case where the independent variable is missing. All right. So they go through this argument, and we're not gonna do it today. We're gonna take a break here shortly. I'm just gonna say see page 73 in 1.6. So when you're looking over section 2.3, read over this section where they solve that second order equation and come up with a general solution for what's called the escape velocity. The question was, with what velocity must this object be shot upward? So no other impulse after that, just an initial impulse shooting it upward. With what velocity would it have to leave the Earth in order to escape the gravitation? That's the escape velocity. So they solve that, come up with a general solution involving G and M. So it doesn't have to be the Earth, it could be another, like the moon or another planet, and G, in terms of M and G. All right, so for now, let's go ahead and take a break. 10 minutes, we'll start at 2:55.